Hi everyone, this is Mrs. Mesoff. We're going to do a few more examples talking about continuous functions just to make sure we really understand that concept and all the different ways we could ask you to kind of show us that you understand. Alright, so for this first example it says, given the graph, answer the following questions. And here's the graph of f of x. Okay, part A says find f of 2. So f of 2 means where is the function defined when x equals 2? Well, if I go to x equals 2, I know a lot of people can get confused, but this is a hole. That means it's not defined there at x equals 2. It's only defined where there's a closed point. And so this is where it's defined at 2, and the y value would also be 2. So f of 2 would equal 2. Okay, for part B, now it's saying find the limit as x approaches 2 of this function. Remember, for limits, I don't care what the function definition is. I just care where it looks like the graph is headed at that x value. And at x equals 2, this graph looks like it's headed for this y value, which would be 1. And so that means that this limit would equal 1. Alright, so then in part C, when it says, is f of x continuous at x equals 2, and explain, well, remember the definition of continuity at a point, specifically an interior point like we have here, is that the limit as x approaches that value has to equal the function definition. So here, since the function definition is 2 and the limit is 1, those aren't equal. So I would say no, it's not continuous at x equals 2. And to explain, I'm just going to use the definition, and that is because the limit as x approaches 2 of the function does not equal the function value. Alright. The last question is just to kind of make sure we recognize some of our interval notation and we're being careful. Letter D, it says, is f of x continuous over the interval 2 to 4? And notice the brackets, that means we are including 2 and 4, right? Include x equals 2 and x equals 4 because they're brackets. And since we're including x equals 2 and x equals 4 on my graph, I'm looking at this part of the graph, including the endpoints. Alright, and because at x equals 2, we just said it's not continuous there, that means this interval we would say no, because it's not continuous at x equals 2. Right? Because not continuous at x equals 2. If we were asking about the interval, if we were asking about the interval from 2 to 4 excluding 2, then it would be continuous. Right? So you just have to be careful with some of those details. Okay, just some other side notes to mention about this graph. Right, at x equals 1, we should notice that's a jump discontinuity because I jump from one value to another. Alright, but at the other endpoint, so at x equals 0, that is continuous because the limit as it approaches 0 from the right equals that function value, and same with the opposite endpoint. Alright, so just some tiny things to kind of pay attention to. Alright, let's do another example. Okay, so in example 2, it says, find each point of discontinuity and identify which are removable. Alright, the only discontinuities that are removable are holes. So if you can identify whether your function has a hole or not without graphing it, then perfect. That will tell you the discontinuity and it will tell you that it's removable. Pay attention to other points of discontinuity, so vertical asymptotes are points of discontinuity. They are not removable. Or if you have, a function that graphs and you notice there's a jump discontinuity, that's also not removable. So the only ones that are removable are holes. Alright, in this function, since it's a piecewise function, I'm going to draw the graph in order to understand exactly what's going on here. Okay. Alright, so this first piece, 1 minus x squared, I like to think of that as negative x squared plus 1. because that tells me my transformations very easily. All right, negative x squared plus 1, so that's going to be a reflection with respect to the x-axis, and then a shift up 1. All right, so normally a parabola I know would have points at 0, 0, negative 1, 1, and 1, 1. I'm flipping that upside down basically, and then shifting it up 1. So now I'll have a point here, and points right here. All right, so this graph would look something like this, except notice how that's for every x value except negative 1. So actually at negative 1, there should be a hole there. All right, the rest of the graph is just going to be a parabola, but at negative 1, we have a different definition. Right? It says if x equals negative 1, the function is equal to 2. So now I'm going up to 2, and that's the point when x equals negative 1. So there's my graph. All right, now it says find each point of discontinuity and identify which are removable. Well, from this graph, hopefully it's pretty obvious that at x equals negative 1, there's a discontinuity. So discontinuity at x equals negative 1. And because that is just a hole, right, the rest of this graph continues on. It is purely a hole. That means we would call it removable. The idea of removable is I should be able to kind of put that hole back, and then the function becomes continuous. That's how you know it's removable or not. If you can't fix it, right, with just putting that 1 point back, then it wouldn't be removable. All right, so this is a discontinuity at x equals negative 1. And then I would say removable because it's a hole. Right, and holes are the removable discontinuity. All right, so if you can tell the points of discontinuity without graphing it, then that's fine. But a lot of times with these piecewise functions, drawing the graph is very helpful. All right, let's do one more example. I'm going to flip it over. Actually, it's on a new page. All right, example 3, it says give a formula for the extended function that is continuous at the indicated point. When it's asking us to do that, that's basically saying the original function we give you is not continuous, but the discontinuity is removable, and therefore you can turn it into the exact same function, but that is continuous. All right, so basically what we're saying is in this function at x equals 1, there's a hole, and I want to take that hole away to turn it into a function that's continuous. All right, in order to take holes away from rational functions, we need to factor. And I know on the bottom here, that's x plus 1, x minus 1. But I know a lot of people get stuck on that top function, x cubed minus 1. The good news is, based on the wording of this question, I know that there's a hole at x equals 1, which means one factor on top has to be x minus 1. And so this came up in another day's notes. If you needed to, if you forgot how this factors, you could just synthetically divide by x minus 1. And whatever you're left with is the other part of the factor. Okay. If you remember how to factor your difference of cubes, that would be obviously a little bit quicker. And this is how it would finish factoring. Okay, a difference of cubes, so that's something like this. That will always factor into a minus b, and then a squared plus ab plus b squared. Okay, not the most important formula to remember, but it certainly does show up from time to time, so if you can remember it, obviously that'd be ideal. But if not, synthetic division will work. All right, so now in this function, both x minus 1s show there's a hole there, so I'm going to simplify. And the function that I end up with, which would be x squared plus x plus 1 divided by x plus 1, that function should, we can double check on our calculators, but this function should be the exact same graph as the original function, but it is actually defined at x equals 1. All right, so this would be my extended function. All right, and to prove that's the case, I'm going to show you on my calculator how we could kind of double check ourselves. All right, I'm going to graph these. I know it might be a little hard to see, but in the top y equals, I have the original function, x cubed minus 1 divided by x squared minus 1. And in the second spot, I have my extended function that should make it continuous. All right, and so I'm going to graph these to show you that they are the exact same graph. Although there's one problem with graphing it, and that is you can't really see holes on the graphs on your calculators. So I can see these graphs are the same. They graph right on top of each other. But the way to really test it is I'm going to go into my table. And in my table, and again, I know it's kind of hard to see, so feel free to do this on your own. But if I scroll to where x equals 1, I can see that in the original function it says error because it's a hole, but in the new function it actually gives a definition. All right, all other points are exactly identical. That's the only one that we've changed by taking out the hole. Okay, so just some nice ways to kind of double check yourself as you're getting used to how these problems work. All right. Okay, that's all the examples for today. If you think of any questions, feel free to write them down, email your teacher, and make sure you're really understanding this stuff. Thanks for tuning in.